So Shubhayan,
Yes.
yeah. So Aseem has joined. So can we test?
So I just a moment.
So Shubhayan.
हाँ एक मिनट हाँ
Yes. Yeah. So Aseem has joined. So can we test?
So I have made you a co-host. So if you want to just share the slide your
So
screen, so you
Aseem
can.
has joined. So can we test?
Yes, hi Shubhayan. I will just do this 1 second. Is this visible?
Yeah, it is visible.
Yes.
But it is not in full screen.
Yeah, it is not in full screen.
So I have clicked that, but it is not doing anything. So let me just 1 second. Let me just restart this maybe. It seems to have hung. Oh, it has gone behind somehow.
So if you minimize it, will it help?
Let me just see. Again. Okay, is this better?
Yeah.
And now I can see myself. I can minimize this. Okay. And hide the controls. Maybe it will just go away on its own. So I just want to check one thing. Are you able to see my cursor when I move it?
Yes. Yes.
Okay. Okay. Perfect. And then you can see the images
Yeah.
here.
Yeah.
So I don't have any movies.
Huh,
So
okay.
fine, I
So
think.
that should help actually. Sometimes when there are movies, there is some problem at times.
Yeah, it can hang. Okay.
Yeah.
So
Yeah.
I
Yeah.
at my end whenever you want to start.
Yeah. So we'll unfortunately, yeah, there was this quiz of the first year BTech students,
I see, I see.
and that we didn't know about when we scheduled this for 6:30.
Uh-huh.
And
Right.
like,
Yeah, so
yeah,
65 even slightly later. So.
yeah. So we'll start at 6:45 p.m.
Okay, okay.
Yeah. Yeah, the thing with first year quiz is that it's very difficult to reschedule it because there are some 600 odd students.
I understand too many constraints. Yes. Yeah.
Shubhayan,
Yes.
Aseem is not able to unmute. So can you just check?
No, it's fine. It's fine. That was an earlier message.
Oh, okay. Okay.
Yeah. After that, he made me co-host now.
Yeah. Okay. I just saw it. So.
No worries. Someone is annotating the screen. So I think maybe you have to disable annotations. They're drawing pictures on my screen.
Oh, that was not you.
No.
Oh,
Okay.
The annotations have not been disabled, so maybe it should be done.
Just a moment. I hope they are not able to now do this thing.
We'll see.
Shubhayan, if like someone wants to ask a question,
Yeah, so that you can just
so one option is to type in the chat box.
one option is while they want to write anything in the chat box, they should write their name also.
Yeah.
Otherwise, it would be difficult for us.
Yeah, that would I think automatically come. But is there a option to raise the hand?
So there is the option. No?
Okay, I cannot see it. So yeah, I cannot see it. Where is that option?
Just a moment.
In reactions.
Mm.
In more on the top
Oh,
right.
yeah, reactions. Yes.
Maybe,
Yes.
so since my screen is full, so
Hmm.
if someone wants to ask a question in the middle, maybe either Shubhayan or Rakesh,
Yeah, I'll be taking care of that.
so you can just interrupt me whenever.
Yeah, yeah.
Generally, people ask questions in the middle.
Sometimes they do. And I also at times decide like if the question is really pressing.
Yes. Okay.
Yeah.
I'm fine either way. So,
Okay.
and you will be recording this for later use by the participants?
Yes.
Yeah. Okay. No, that's good because some slides will be somewhat fast, so then it'll be good if
Huh.
anyone has to go back to them.
So just for the participants who might have missed the start time, the new start time is 6:45 p.m. So we'll wait for another 3-4 minutes and then we'll start. So should I start?
Yeah, you can start. And you can switch on your...
Yeah. Okay. Hello and welcome everyone to this fourth colloquium in this LNMIIT online colloquium series. It gives me immense pleasure to introduce today's speaker, Professor Aseem Paranjape from IUCAA, Pune. So, Professor Paranjape did his master's from St. Xavier's College, Mumbai, after which he joined the Tata Institute of Fundamental Research, Mumbai, where he did his master's as well as his PhD. After finishing his PhD from TIFR, he went for his postdoc to ICTP in Trieste, Italy, and he also did another postdoc at ETH Zurich. After his postdoctoral fellowships, he joined IUCAA Pune as a faculty, and he has been there since then. And Professor Paranjape's primary area of work is on understanding our universe at its largest scale. And in addition, he also likes to work in applying statistical tools for understanding various aspects of astronomy and astrophysics. And these days, as he informed me, he is also interested in some aspects of machine learning. On a personal note, I can say that I have known Professor Paranjape for about 21 years. So we both started our PhDs at around the same time under the same supervisor. Aseem joined 1 year after me, and we had we used to have several interesting discussions on whatever we were doing, and we used to exchange our ideas. And so it's a special for me. It gives me a special pleasure to have Professor Aseem Paranjape giving this colloquium. So without much ado, I'd like to invite him for telling us about universe at its largest scale. Just a word for participants and the audience that if you have any questions, if the best would be you just type the question in the chat box and I'll take up the question. Or if it's a very pressing question and you want to directly ask the speaker, you just raise your hand and I'll allow you to ask the question. Okay. So Aseem.
Thank you, Rakesh. That was a very kind introduction. And obviously, when Rakesh asked me to give this talk, there is no way that I could say no. And he has already explained why that might be. All right. So I understand this is mostly an undergrad audience. There is the obvious disadvantage of the online format where I cannot see your faces. I usually like to see the faces of people in my audience to understand when they are falling asleep and when they are not understanding various things. But as Rakesh has said, please feel free to stop me and ask questions at any point where you think I am either going too fast or if something has not been clarified. Okay, so I have organized this talk as a sequence of stories because when I was growing up as a PhD student, one of the things that I found fascinating was the history of this subject, apart from the inherent interest in the science itself. So I have tried to organize things in this way where we will go historically, but it will not be always a sequentially chronological history because there will be several stories which are interesting in this context, and I will try to tell each of them at the appropriate point. So to set the stage, let us try to understand what length scales one is talking about in this discussion. So the smallest length scale that one can reasonably imagine using in this context is the astronomical unit, which is the average distance between the Earth and the Sun. And as you might know, I'm sure from your BSc textbooks, that the distance between the Earth and the Sun is around 150 million kilometers. Okay, and this is called one astronomical unit. So our solar system is of the order of 100 astronomical units or so. And the distance to our nearest star is of the order of substantially larger than that. It's of the order of something like 100,000 astronomical units. Okay. And at that point, it stops becoming useful to use astronomical units, even though it is already a very large number. And one maybe starts using something like light years. Okay, so how much distance is covered by light in 1 year? That is 1 light year, and that is about 10 to the 13 kilometers. Our nearest star, as you know, is about 4 and something light years away. For cosmologists and astronomers, light year is sort of a popular science kind of unit. We like to use something slightly different. It's related to the light year. Unit-wise, it is very similar, but it has a different geometric definition. This is called the parsec, and this is roughly 3¼ light years. Okay, and I'm sure you have come across the definition for parsec. It has to do with when the Earth goes around the sun. If I look at a distant star, as I see it, there will be a parallax, and if I can measure what angle this parallax is making, I can use it to convert it into a unit of distance, because I know the size of the orbit of the Earth around the sun. So that's 1 parsec. So typically, few parsecs is the distances to nearby stars. The next interesting scale in the problem is, we know that stars are organized into galaxies. We live in a galaxy. It's called the Milky Way. This is an artist's impression of the Milky Way. So typical galaxies have sizes which are of the order of few tens of thousands of kiloparsecs, of parsecs. Okay, so 1,000 parsecs is called 1 kiloparsec. And galaxies are something like tens of kiloparsecs in size. So you can rapidly see that how we are moving really far away from our comfort zone. Earth, sun is something we can maybe get our heads around, but now we are going to tens of thousands of times these distances. We are not going to stop here. The galaxies themselves are organized into larger conglomerations called groups and clusters of galaxies. And these clusters, so this is a very famous cluster of galaxies called the Coma cluster. These clusters are typically few thousands of kiloparsecs in size. Okay, so 1,000 kiloparsecs is 1 megaparsec. And these clusters of galaxies are of the order of a few megaparsecs in size. So now we have come to pretty big scales where now individual galaxies are starting to look pretty small. Okay, so inside this kind of galaxy, there is probably this kind of structure. In here, there is probably a star which looks like our sun with its solar system around it. So this is the progression of length scales we are talking about. And we are not even going to stop here. Okay, so our story actually does not even start here. So we are going to start at an even larger scale. This is the first kind of segment in our story that I would like to tell, which is, I will call it the nearby universe. Nearby is something of a joke compared to what we have just been talking about. Okay, but for a cosmologist, what the nearby universe means is things which are of the order of hundreds of megaparsecs away from us. Okay, so remember what we said, 1 AU, 1 parsec, 1 kiloparsec, 1 megaparsec. And now we are going to say, what are all the things, all the galaxies which are within of the order of 100 megaparsecs from me? That is what I will call the nearby universe. Okay, so how was this nearby universe? How have we progressed in our knowledge of what this nearby universe looks like? So this part of the story started in the mid to late 1970s, around 1978, 79, when there was a survey done of galaxies in the sky at different distances from us. And it produced the following result. Okay, so the way this plot is organized is that on this radial axis, there is distance away from us. It is recorded in some weird units, but I will explain this in a second. But for the time being, you can think of this as distance away from us. Okay, and this axis is angle in the sky. And what you have done is you have taken a patch of the sky, and in the sky there are 2 angles, right ascension and declination, theta and phi, if you like. So you have collapsed one of them, and you're showing the other one. Okay, so this is this plot. And this image was a remarkable surprise for the scientists who made it and for the community in general, because until this point, it was not clear how galaxies are distributed in space. And people had generally believed that galaxies are distributed randomly in space. There were ideas, especially by people like Vera Rubin, who I will mention later as well, that galaxies are probably clustered in space, that where there is one galaxy, there will likely to be other galaxies. But these were not taken very seriously around the early 70s or so. So this late 70s discovery of our neighboring patch of the universe was actually a remarkable breakthrough. And you can see this famous stick man-like image. These are all, by the way, individual points are galaxies. Okay, each point is one galaxy. So this was one slice from this Center for Astrophysics CFA survey. If you take 6 of them and stack them together, it starts looking something like this. So now you can see that not only are galaxies distributed not randomly, but they form interesting patterns. And these patterns are actually at very large length scales. So what is being shown here is a way of plotting distance. This distance I will come back to in a second part of my story, how this thing becomes a distance. Here it looks like something that is in velocity units. But what you can imagine is that this point here, so roughly 3,000 kilometers per second, is something like 100 megaparsecs away from us. Okay, so this is something like a few hundred megaparsecs away from us. And this structure here, for example, this very thick structure here, this is called the CFA Great Wall. Okay, so it looked like a wall of galaxies that was surrounding us, and this is what it was named. There is something else that is interesting. Look at this patch here. It looks like there are these galaxies sitting in a line, and this line is almost perfectly radially aligned with our direction. And maybe you can also imagine that there is a similar line here. Okay, so these kind of effects were seen and they were understood only much later. So I will try to talk about them as we go along. So this was one of the first surveys. Remember, this is like early 1980s or so. About 20 years later, our technology had improved. We were in a position to survey the universe better, in the sense that our instruments had become, I think the annotations are still not off. So somebody's still annotating my screen. So the instruments had become more sensitive, which means we could look at much fainter objects in the sky. And money was also being spent in these surveys. So people were able to spend more nights at the telescope observing the sky. All of this meant that the number of galaxies that we could observe and the volume of the universe that we could cover had increased dramatically. So this particular survey is called the 2DF, or 2-degree field. 2-degree field comes from the instrument which had a 2-degree field of view in the sky. So this is the 2-degree field galaxy redshift survey. And this was among the first surveys. So it surveyed several patches that look like this. Here, just for pictorial representation, they have put 2 of them end to end. But it observed something like 400,000 galaxies. Okay, 4 lakh galaxies were observed. Again, each point is a galaxy. And now you really start seeing this beautiful pattern where things are definitely not random. There are places where there are many, many galaxies. There are these filament-like patterns, like a web, a spider's web, which is connecting these galaxies together. And then there are these regions, very large regions, where there are almost no galaxies seen. Okay, and here, for example, you see this large patch where there are very few galaxies. Now you might say, okay, maybe there are all these galaxies are there, they're just too faint, and that's why we weren't able to see them. The point is that there are even further away galaxies. Remember, this axis is distance away from us. So there are galaxies here which you are able to see, right? There are lots of them here. And your surveys, your instrument is sensitive enough to detect them. So it should have been able to detect galaxies here if they existed. And the fact that you don't see them means that they don't exist. Okay, so there are these large voids which are also seen. And here, for example, you can see this axis which is called redshift. I will talk about this again as we go along. Just to make a point here that this quantity called redshift is basically a linear relation in distance. So whether you talk about redshift or distance, it is basically the same thing here. There is just a mapping that you need to understand how many light years or how many billion light years corresponds to what redshift. And again, like I said, 0.1 is roughly like 300 megaparsecs or roughly 1 billion light years. Okay, so this is the kind of map that the 2DF Galaxy Redshift Survey made for us. And this survey was one of the first surveys to use large-scale structure to perform cosmological measurements. So we understood things about cosmology based on this survey. Okay, this was one of the first.
So, Aseem, just one thing. So, if I understand correctly, you will be explaining a few things about the map that we see here, like why there are these filamentary structures, because there was this question whether there is any reason why there are this filamentary structures.
So, so I will come back to this a bit later in the talk, maybe in the second half of the talk. One of the main questions that we would like to ask in this community is what leads to this filamentary structure. So it is in fact one of the most important questions. This is not a new question. It has been there since the 1980s when this first survey was produced. And there has been a lot of work on this, and today have a very good understanding of why this structure emerges. So I will come back to this point, but there are still several interesting things about this which are not known, which I may touch upon as well. Okay, so this is what I want to do right now is just tell you what exists, and then how we understand it is a later part of the story. So this survey, the 2DF GRS, was around 2001 or so. It was overtaken by another survey because by this time there was a lot of interest in these galaxy redshift surveys, and especially in the US, the government was being convinced to put in some money to perform even deeper and wider versions of these surveys. So that is what led to what is called the Sloan Digital Sky Survey, or SDSS. This was a path-breaking survey in the field of extragalactic astronomy. It changed the way we look at the universe in many different ways. I will focus only on the large-scale structure. And basically, what you see here is an image that looks very similar to the previous one. Okay, so visually, there is not much difference. If I look at redshift 0.15, I can see that there are a lot of galaxies observed up to about 0.15, and then they drop off because they're too faint to be seen. Here, the redshift axis only goes to around 0.15, and again, you can see lots of galaxies are observed. So the distance away from us that we could reach was similar in this survey and in the previous one. But there were two critical differences. One is that the sky area that was observed in the SDSS was about 10 times larger than the sky area that was observed in the 2DF. So these kind of plots are a little misleading because you always see only these two pies in the, two slices of the pie, but that's just for representational purposes. What you really have to ask is, when I look at the sky, there is the entire sphere, which is like 41,000 square degrees. Okay, and what fraction of that sphere was I able to observe? So here, people were able to observe around 1,500 square degrees. And here, over some 15 to 18 years of observations, that number has gone up to about 15,000 square degrees. So about 10 times larger in area. And therefore, because the distance is the same, also about 10 times larger in volume. So already that tells you that the number of galaxies you have observed should be about 10 times larger. And actually, that is not completely correct because the number of galaxies was even more than 10 times larger, because the second breakthrough was in how faint a galaxy can you observe. Okay, and here the kind of galaxies that were observed were substantially fainter than the ones that could have been detected in 2DF. So the actual number of galaxies seen here was something like 4 million. It was close to 17 to 20 times larger than in the 2DF survey. Okay, so here we are now really talking about very, very deep and accurate maps of the universe. So this is like saying a Google map of the universe with really precise location accuracy on where every galaxy is and what everything is doing. And again, you see this beautiful filamentary structure, very dense regions with large voids organized in this so-called cosmic web. So this cosmic web was actually a theoretical prediction from the 1990s, and it was revealed by these surveys. Today, Okay, so this is still.
So Aseem, just one question.
Yes.
So we see some two wedge kind of structures where there is a lot of there are a lot of features, and then along the horizontal line you don't see anything.
Yes.
So what is the reason for
This
that?
is again just a representational issue, because what has been done is the way the survey is done is to take patches in the sky, and then what you do is you just create a little slice like this, okay, and then you plot one slice. And now if I just plot one slice, then the rest of the plot looks kind of empty. So I show one more slice. But now if I start showing more slices like this, it'll appear to you as if the universe is kind of circular, and then you'll start seeing discrepancies between this slice and the one in between and the one in between here. So usually when you show these things as a visual exercise, you tend to show just two. But of course, there are not just these two slices. And you have to imagine that there is a third axis also, right? So there is the theta phi, but here only theta is being shown. The phi direction is not shown. So really there is a 3D view in which these galaxies are fitting in. Maybe the next one, okay, I'm sorry, I don't have a 3D version of this. But if you go to this website, sdss.org, there is a gallery where they have many images, including 3D versions of these things. And they show you exactly how these slices were constructed.
Okay.
It's not that the universe is empty here. It's just that you're not showing patches according to your convenience. Okay, so this is still SDSS and its subsequent versions. So the SDSS evolved into something called the BOSS, which stands for Baryon Oscillation Spectroscopic Survey, and its extension called EBOSS, Extended BOSS. Okay, so basically baryon oscillations, this is a technical term in cosmology. The idea is that the structure, the distribution of these galaxies, it's more clear here. This is not random. Okay, so this is obvious from looking at the plot. What you can do is apply some statistical techniques. And the most basic statistical technique is called the two-point correlation function, basically asking, if I observe a galaxy here, what is the likelihood that there will be another galaxy which is at a distance of, let's say, 10 megaparsecs away from me? Then given the galaxy here, what is the likelihood that there'll be another galaxy 100 megaparsecs away from me? Okay, and so as a function of distance away from us, you can keep asking this question: what is the likelihood that there'll be other galaxies so much distance away from me? This kind of question, the answer to this question is called the two-point correlation function. And this is a statistic that is routinely measured in these galaxy surveys. It is also a statistic which is routinely predicted in theoretical models of the universe. And one of the things that theory predicts is that when you plot this two-point correlation function, which is shown here as a function of distance or as a function of separation, there is a predicted bump that is expected to be seen around 100 megaparsecs, okay, 150 megaparsecs. So what is being shown here is that these SDSS and its later cousins, they were observing different kinds of galaxies, and in each type of galaxy, they were measuring the two-point correlation function, and they were seeing that there is this particular feature. Even if you forget about the lines, which are the best fitting models, in some of these, in this one, in this one, in this one, you can see the feature by eye, right? You don't need to do any complicated statistics to see that there are points here, and then there are more points here. Here, it is very clear that there is a bump here. Okay, so this bump is a prediction of standard cosmology, and it is a way of measuring distances away from us, a particular kind of distance away from us. So this is something that is a very crucial target for surveys which want to use galaxy distributions to perform cosmological measurements. And this was one of the main primary science drivers of the SDSS and its successor, especially the BOSS surveys. So you can see here the timeline as well. SDSS started in the late 90s, early 2000s, and it has had a 20-year history of collecting data. And what you can also appreciate is how far we have now been able to map the universe. This is a slightly different way of plotting look back time. Let's not worry about this for a second. But what I want to emphasize is look at this green patch here, right? This is SDSS nearby galaxies. This patch is the same as this patch. Okay, it's basically exactly the same patch. So this is like a redshift of 0.15. What I told you is redshift 0.1 is 300 megaparsecs. Okay, so 0.15 is 1.5 times larger than that.
450 megaparsec. So this little green patch is 450 megaparsec in radius. And now you can imagine, scale this thing up. Okay, so this is how far we are seeing things. This is like 5 to 10 times larger than this original SDSS patch. This is what we have been able to do with 20 years of observation in the SDSS and EBOS campaigns. People have not stopped here. The cosmology community is continuing to perform large surveys. So the latest such survey is the DESI survey, the Dark Energy Spectroscopic Instrument, DESI, DESI. And this one has changed the game in terms of how many galaxies and how faint a galaxy you can observe. So with the SDSS, we were able to see 4 million galaxies in this nearby sample by the end of the campaign. In DESI, already in the first year of data, you have collected of the order of 2 to 2.5 million galaxies. Okay, and it's like a 5-year campaign, so the data are just coming in rapidly year by year. So this beautiful plot was released by the DESI collaboration, and it represents what they call data release 1, which I think is the first 2 or 3 years of data, if I'm not mistaken, 2 years probably. And what you can see here is something, so this BGS stands for Bright Galaxy Survey. DESI is organized into 4 surveys: the Bright Galaxy Survey, the Luminous Red Galaxy Survey, LRGs, Emission Line Galaxy Survey, ELGs, and QSOs, which is quasi-stellar objects or quasar surveys. So the BGS is what you might call is the closest to the original SDSS. And you can see the level of detail that is there in the BGS sample. And you can also see that just this patch, which is zoomed in here, is so detailed, and it is less than 0.1% of the full survey volume. Okay, so the sky area has been increased. The depth to which we can observe, how faint a galaxy you can observe, that has been increased. And the other important breakthrough here was how close 2 galaxies can be and still be detected as single galaxies, as individual galaxies. This has also been dramatically improved because of technological developments. So I wanted to show you here one plot of a spectrum using which one figures out what is the so-called redshift. Okay, so what this redshift means. Basically, you take a spectrum of a galaxy and you have several emission lines like this. Okay, so there is the hydrogen H alpha line. There are some ionized states of nitrogen. There are some ionized states of sulfur or silicon. I cannot read it here. There are some ionized states of oxygen. Okay, so there are these galaxies in which you take a spectrum. You see these lines. These are lines due to electronic transitions in atoms, and these atoms are well-known atoms. You can study them in the lab, so you know where these transitions, at which wavelengths these transitions are supposed to produce lines. So the lab wavelength is known. The observed wavelength of these features is whatever it is, because you know that if you have a hydrogen alpha line, you will have an N2 doublet coming in this way. So you know that this represents that particular set of lines. So now I can measure the wavelengths of these lines, and I can compare it to the lab wavelengths, what I expect. What you will find is that these wavelengths don't match the lab wavelengths. They're typically larger than the lab wavelengths. So they are shifted towards the red end of the spectrum. That is why these are red shifts. And our theory predicts that this amount by which these lines are shifted in their wavelength is linearly proportional to how far away these galaxies are from us, at least for these nearby galaxies. So that is why this particular quantity called the redshift, it can be used as a trivial measure of the distance. So that's why cosmologists simply don't bother these days even writing the distance in megaparsecs. They simply report the redshifts. Okay, and what you can now see here is SDSS was going out, the original sample was going out to 0.1, and the quasar sample was going out much further, out to redshift 10 or so. Similarly here, the BGS, which is the equivalent of SDSS, the BGS itself is going out to redshifts of around 0.5 or so. Okay, so or 0.4, which is already 4 times further away than SDSS. So this is, I hope it is clear that we have been making steady and dramatic progress in this field of observing what the large-scale structure of the universe looks like. And I will now move on to try to understand or try to see what is the theory in which we can place this entire structure that we see around us. Okay, so now I'm going to shift gears. Maybe this is a good time to take a couple of questions on this part, if there are any.
Yeah, if anyone has any question, you can ask now. Don't hesitate. Either you
Many
can
things, of course, are probably not clear why this happens, etc. Hopefully, they will become a little clearer. But if something I said was not clear, okay, some parts of the plot or something like that, I can quickly take that.
Okay, so I see a couple of questions. One question is, what instrument was used to make the spectrum?
Yes.
And the other question is, how did DESI do the survey? I mean, how did it map the sky?
Yes. So what typically one does is you have large telescopes. These are all ground-based telescopes. So they're very large mirrors, basically. And you know the principle of a reflecting telescope. You collect light in a concave mirror, you focus it onto its focus, and you put an instrument there. So there's a detector which will capture light over there. And then in this detector, you can implant some optical fibers. And these optical fibers can be used to split the light, and then you can pass them through a spectrograph. And then that is how you produce these spectra. So this is a typical journey of a photon coming from a galaxy into our detectors. So what DESI has done, and all previous surveys in this legacy have done, is to use several of these large telescopes. They are primarily based in South America and in North America, and also in, I think geographically these are primarily the places where these telescopes are based. They are run by different countries, usually by the US, also by by countries in Europe, and also by Australia, etc. And then what you have are the scientists in these countries. They are responsible for maintaining the telescopes and also in developing new instruments. So in each of these surveys, there has been technological advancement in the kind of instruments that were produced. So from SDSS to DESI, for example, one major advance was the way these spectra are collected, the way the optical fibers are placed. So in DESI, what was done was you have the focal plane of the mirror, and that's where you place your instrument. Now I have a plate, like a metal plate, which I will place at this location. And I have already done what is called an imaging survey, which means I've already collected some light, and I know that there is a galaxy here, there is a galaxy there. I know the positions of these galaxies in the sky. I just don't have their spectra, because to take a spectrum, I have to really collect a lot of photons. But in order to just figure out whether there's a galaxy or not, I can do it with relatively fewer number of photons. So I first do what is called an imaging survey with fewer number of photons, less amount of time, lots of galaxies detected. Then I say, okay, among these 1 billion galaxies that are detected, there are around 4 million of them, which are good targets for my spectroscopic survey. This is decided by how much time I can spend. So that number 4 million is decided by how much money I have. And which of the billion I should use, that is decided by some complicated algorithm. Okay, so I'm not an expert on that algorithm, but there are ways of figuring out, okay, these are probably good candidates. Now I find my candidates, I know where they are in the sky. So I create a metallic plate. I engineer this plate in which I drill holes at the locations which will be precisely underneath those galaxies. Okay, so light from the galaxy, when I point my telescope in a particular way, light from a particular galaxy will fall precisely on a particular hole. I will place the hole in that way so that my holes match my targeted galaxies. And I will place optical fibers behind these holes. So from each hole, I will have an optical fiber. Okay, so this is the SDSS way of doing things. So now the limitation is how close can you engineer these holes, and how many holes can you build in a reasonable amount of time, how many fibers you can place. So beyond a certain, and how thick are your fibers? Okay, your holes cannot be smaller, and your fiber itself cannot be smaller than a certain amount. So that limits how close two galaxies can be before you start merging them and their light falls into the same fiber. So that was the SDSS way. In DESI, what was done was to firstly change the technology that produced these fibers. So the fibers, I believe, were a bit smaller in size, so they can be placed closer together. The other big advance was that the placement of these fibers was done robotically. It was not done manually by digging holes and then placing the fibers by hand. It was done robotically and in a dynamic way, so that you can, on the fly, you can decide, okay, on this night, I want to observe this one. Tomorrow, maybe there are clouds, I'll not observe that one, I'll wait for some time, etc. Okay, so this dynamic way of doing things helped them considerably in making sure that their samples are very highly complete. And plus there were technological improvements in the way the optical fibers themselves work and so on. So all of these things have helped in producing a much deeper and high resolution image of the universe.
So Aseem, can I take two more questions?
Go ahead.
Yeah, so one question is, in this plot, why are quasi-stellar objects shown on the periphery?
Good. So it is not that they are shown on the periphery, it is just that we observe them like that. So quasi-stellar objects are inherently extremely bright. The physics of these objects is that they reside inside galaxies. They are not galaxies. They live typically at the centers of galaxies, and they are extremely bright sources of light because we believe they are powered by black holes, that supermassive black holes, like million solar mass black holes, which live at the centers of galaxies, and they are driving very powerful jets. And these jets light up the region around them, and they can be so bright that that point-like object can outshine the entire galaxy in which it is sitting. Okay, so they're incredibly bright objects. The other aspect of QSOs is that they are relatively rare in the zoo of galaxies that live around us. So not all galaxies are quasars. They are called quasars for short. So not all galaxies are quasars. There is a small fraction of galaxies which at any given point of time will appear to us as quasars. So now there are these two interesting aspects of quasars. One is that when they happen, they are very bright. The other thing is that they are quite rare. So the rarity of these things means that if I look only in a small volume, the total number that I will see will be very few, simply because they are very rare. So in order to see a lot of them, I have to have my volume to be very large. Okay, so that is one aspect, one reason why I usually don't see them in great numbers close to us, because they are rare. The other thing is that they are very bright, so you can see them even if they are very far away. A typical galaxy is not as bright as a typical quasar. So a typical galaxy, which is in the BGS, will not be seen at a distance at which you might see a typical quasar. So that is why when you make a plot like this, most of your quasars will end up looking like they are very far away, and most of your galaxies will look very close by. But actually there are quasars here also, inside the blue, inside the orange. It's just that they are fewer in number and they are dwarfed by the other samples which are denser over there. I hope that clarifies this thing.
Okay, so last question for now, it is related to the redshift. One is related things that can you explain the meaning of redshift a little more? And the other one is that is it okay to say that this picture, because it's in terms of light coming from different galaxies, far off galaxies. So the picture is actually telling us about time period also.
Good. Okay, so I'll take the question first, the redshift question. So actually they're related question. Okay, so the redshift of an object, for the time being, I will, in fact, in the next few slides, we will talk a little more about this redshift versus distance. But the redshift as a measurement itself, one can try to understand from here. Suppose I take the hydrogen H alpha line. This particular line here is sitting at 7,000 angstroms or something a little bit higher than that. And we know that in the lab, the wavelength of hydrogen H alpha cannot be 7,000. Okay, it has to be a different number. So what you say is that let me take the ratio of the observed wavelength of this hydrogen H alpha line to its expected wavelength. This ratio is a number bigger than 1. How much bigger than 1 is this quantity redshift? So I take this ratio and I subtract 1 from it. What I get is called the redshift. If you remember Doppler effect from special relativity, this effect appears there as well. If I have an object which is moving towards me and emitting light towards me, the light that it emits will be blue shifted. Similarly, if an object is moving away from me but is emitting light towards me, when I get that light will appear to be red shifted. So it is a very similar effect, but the cause is different. Okay, so the cause we will come to in a second, but this at least hopefully explains why when in 1978 and 1980, when people plotted this kind of plot on the axis here, they didn't even show redshift. They multiplied it with c, speed of light, and they plotted things in kilometers per second. Okay, so this was because there is this ingrained intuition of the Doppler effect, which where you just take the redshift or blue shift and you multiply it with speed of light, and it gives you an estimate of the velocity, relative velocity of this object. Okay, so there is a naive way in which you can think about this plot, that this is telling you how fast these galaxies are moving away from us. But that is a flawed way of thinking, what for reasons I will discuss. What one should remember here is that what is actually being measured is this quantity Z, which is the redshift. It is just the ratio of observed to emit of the observed to expected wavelength -1. Okay. The other issue was is distance away from us also telling us about time? Absolutely, it is, yes, because light travels at a finite speed. So if I see today a galaxy which I can observe at a distance which is so much far away from us, it also means that the time at which this light was emitted is earlier than the time at which the light from this galaxy was emitted. Okay, and in fact, in this earlier plot, they showed something called look back time. This is exactly this time. Okay, so how far back in the past was the light emitted? So this SDSS is somewhere here. Okay, and this is somewhere here. So for example, these galaxies, which are these luminous red galaxies from BOSS, they were emitted, the light from them was emitted 5 billion years ago. Okay, and today we are seeing this light. Yeah, so I hope that answers this question. Is that okay?
Yeah, I think this is okay.
Okay, so let's move on. I think I'm going very slow. So at some point, Rakesh, you can just tell me, okay, it's getting late and we can stop. So we'll reach some point in the story. Okay, maybe it's not complete, but that's fine.
Okay.
Okay, so let's do a little historical tour of the theories behind our understanding of the universe. So this part I call the expanding universe. I like this story very much. Okay, so I like telling it as well. So the story begins with Einstein. Many good stories should begin with Einstein. Einstein was the genius of our times. Of course, he did many things. He became famous already in 1905 with special relativity and all the other things he did, Annus Mirabilis. In 1915, he published his final version of the general theory of relativity, and he was super excited about it. He started applying it everywhere. In 1916, Carl Schwarzschild presented him with the first analytical solution, using which was the Schwarzschild solution, using which Einstein started making predictions from GR, and many of these predictions were tested later, etc. But for our purposes, for cosmology, one of the interesting things he did was in 1917, he published a model of the universe in which the universe contains matter. It contains a cosmological constant. It also contains something called spatial curvature. And he adjusted the amount of matter and this cosmological constant, which is just a constant in his equations, and the spatial curvature. And he very precisely tuned the values of these quantities so that this universe remains static. It does not change with time. Okay, so this was his it was his version of what cosmology should predict for the universe. Okay, so this was one of the starting points of cosmology. Observationally, there was something else that was happening. Okay, so this is Edwin Hubble. He was like the rock star astronomer of his times. Truly amazing person. So in 1924, he presented a remarkable result. He proved that certain nebulae, which were observed in the sky and whose origin was unknown until that point, he proved that those nebulae are actually not inside our Milky Way. They are themselves galaxies which are far away from the Milky Way. Okay, so the way he did this was to use something called Cepheid stars, Cepheid variable stars. So Cepheid variables had been recently discovered by Henrietta Leavitt. And these are stars which pulsate. and their size increases as a function of time, and it oscillates as a function of time. And this pulsation period is related to how intrinsically bright they are. So what one can do is to say, okay, I see a CFIT, it's pulsating, and in my galaxy, I have other ways of determining distances. So for this CFIT, I'll figure out how far away it is. So I see that it's pulsating. I know how far away it is. I can also see that it has some apparent brightness. So I can convert the apparent brightness and the distance into an intrinsic luminosity. And I can therefore find that there is a certain relationship between the luminosity and the period of these CFITs. Okay, so this is this remarkable property of CFITs, that their pulsation periods are related to their intrinsic luminosities. So I calibrate this relation in my galaxy, in the Milky Way. Now I can see CFIDs everywhere else in the sky, and I can see them pulsating, and I can also see they are apparently faint. Okay, so I can use the calibrated relation between period and luminosity to figure out what is the intrinsic luminosity of those CFIDs that I'm seeing now as faint objects. And the fact that they are faint tells me that they must now be far away. So I can calculate how far away they are because I know their intrinsic luminosity from their period. And I know how faint they are because I observed them in the sky. So I can use CFITs to figure out how far away these objects are. And Hubble showed that these CFITs that he found in these nebulae, they are not at distances which are commensurate with the known size of the Milky Way. They are orders of 10 times larger than the size of the Milky Way. Okay, so they must be outside the Milky Way. So in this very real sense, he expanded our understanding of the universe, literally expanding the universe and saying that there is a universe. Milky Way is not the universe. There are island universes, which we can call different galaxies. So he could have stopped there, okay, and he would have been famous for the rest of his life. Can someone please stop annotating? Thank you. So he could have stopped there. It would have been absolutely fine, but he went ahead. He collected together these distances from the CFIDs in these distant galaxies. And he also had measurements of redshifts to these galaxies. At that time, measuring redshifts was a very tough thing to do and a very, very nascent field. It was painstaking to produce a spectrum of a single object, hours of work. And Vesto Slipher was an astronomer who had been doing this. So Hubble collected the results of Vesto Slipher. He added a few more redshifts of his own. And he produced this plot. Okay, so in this plot, on the x-axis, he put distance, calculated using distances to CFITs. And on the y-axis, he put what we would call c times z. There is a typo. He wanted to write kilometers per second, but he wrote kilometers instead. And anyway, so this was the redshift times velocity of light. This was the distance. And what he noticed is that more or less, okay, there's a huge scatter, but he was brave enough to say, let's plot a line through this. Yeah. And it seems, therefore, that if I have galaxies which are further away from me, then their supposed recession velocities are larger. So there seems to be a monotonic relation between distance and the recession velocity. Like I said, recession velocity is now, we know, the wrong way of thinking of this. What he was measuring was redshifts. So there is a linear distance between distance and redshift. Okay, so this became famous as the Hubble law. So this was 1929. So try and keep these dates in mind. 1915, GR. 1917, Einstein presents static universe. 1924, we know that galaxies are galaxies. They are not part of Milky Way. 1929, linear distance redshift relation is published by Hubble. Okay, let's proceed a little bit further. So now, chronologically a little bit shifted. So this is somewhere in between Hubble and Einstein. 1922, Alexander Friedman. He was at Einstein's theory, and he presented a couple of models. So one model that he wrote down was called the closed universe, in which he showed that under very general circumstances, the size of the universe can increase initially and then eventually turn around and decrease. And then the universe can actually recollapse. And he had this closed universe model in which there was matter and there was also this cosmological constant that Einstein had introduced. And what Friedman pointed out is that Einstein's solution was a very special case of the ones that he was talking about, and his were more general. Einstein was not at all happy with this. Okay, so in fact, he initially claimed that Friedman's algebra was wrong. Now imagine, I want you to imagine that you are like, okay, you probably cannot imagine that you're in your mid-30s, but maybe you're in your early 20s. Okay, that's not so far from mid-30s, right, as in terms of age. So you have written this, you have seen Einstein's paper, and you have said, okay, let me use Einstein's theory to write down my own solutions. Yes, and I have come up with this algebra. I have the courage to say that Einstein's solutions can be generalized, and I send my paper to Einstein for comments. What does Einstein do? He says your algebra is wrong. I personally cannot imagine something that would be more, I would be so dejected. It would be so discouraging to hear such a thing. But Friedman kept at it. He was confident of his solutions. He wrote back to Einstein. They exchanged letters. Eventually, Friedman convinced Einstein that his algebra is actually correct. Einstein published a retraction of this statement that Friedman's algebra was wrong. So Einstein accepted that the algebra is okay, but he was not happy with the physics of this solution. In 1924, which was the same year as Hubble's observations of Cepheids, but 5 years before the distance redshift relation. Okay. So in 1924, Friedman published another solution in which the universe keeps expanding forever. Einstein was not happy with this also. Einstein's role in this story was very interesting because he was hell-bent on ensuring that the universe remains static. He simply did not like a universe which changes. Okay, it was against against the fiber of his being that the universe can change. Okay, because also there were not many observations at the time. The tragedy of this story is that Friedman died in 1925 at the age of 37, 4 years before Hubble's results were published, and which would eventually confirm that Friedman's models actually are the correct way of thinking about the universe. Okay, so this was a really sad chapter. Then comes the incident of Georg Lemaitre. Georg Lemaitre was one of the most fascinating characters in cosmology around this time. Okay, so he was a Belgian Catholic priest, and he was studying cosmology. He, like Alexander Friedman, he was also impressed with Einstein's work. He knew about Friedman's work. He used Friedman's work in 1927, 2 years before Hubble's paper. Okay, Lemaitre wrote a paper in French. In this paper, he did remarkable things. First of all, he explained that in a cosmology which is given by something like Friedman's equations or Einstein's equation, you can actually explain redshifts of galaxies as a consequence of expansion of the universe. Okay, that redshifts are not something that are strange in this setup. And redshifts, remember, were known. Hubble had already published, Hubble had been taking redshifts already between this time 24 to 29. Westo-Slipher had published redshifts. Hubble was also publishing redshifts. Next, in the same paper, he pushed that calculation further, and he theoretically predicted the linear relationship between distance and redshift. Analytical calculation, okay, not through observed data. Then, being the roundabout, the fully rounded scientist that he was, he did not stop there. A theorist would have said, fine, now observers can go and check. Lemaitre said, there is data already. Hubble has already published some data. Okay, let me take this data. He actually produced a plot which was basically the same as Hubble's original plot. And he drew exactly the same conclusions that Hubble later drew in 1920. He also measured the slope of this relation, 500 kilometers per second per megaparsec. And Lemaitre also got the same number. Moreover, he then constructed a solution of Friedman's equations with non-zero lambda in the attempt to explain all of this data. Okay, so all of this was in a 1927 paper written in French. Nobody read it in the US because it was written in French. Okay, it got ignored. There's a very interesting conclusion to this history also. You can ask me in the questions if you like. But I just want to focus on Lemaitre's theoretical contributions. In 1931, he presented another model universe in which cosmological constant was adjusted in such a way that you can solve what was then called the age problem. Okay, so the age problem is very fascinating because there is this constant, this slope, 500 kilometers per second per megaparsec, which is the slope of this diagram. Now, this is an observational fact, okay, that this slope is this. So now what happens is this slope, if you look at it, the way it's measured is a bit strange, but the dimensions of this quantity are 1 over time, right? Because the kilometers and megaparsec are both lengths. So this was 1 over time. So if I take 1 over this quantity, inverse of this quantity, it's a quantity of units of time. So now in this Einstein-Friedman kind of way of thinking, the inverse of this slope becomes an estimate of the age of the universe. So now you can do this calculation yourself. If I take 500 kilometers per second per megaparsec and I take 1 over this and I ask what is this number in years, it turns out to be a number which is 2 billion years, 2 gigayears. Now, if you remember your basic astronomy from somewhere, you will know that the age of the sun is known to be much larger than this. It is at least 4.5 billion years. It is almost exactly 4.5 billion years. We know this, okay? So 2 billion years cannot be the age of the universe because there are objects like the sun which are older than that. So there was an age problem in this period. And Lemaitre was constantly thinking of trying to make things consistent. So he had invented this model in which you can have a period where the universe almost does not expand for a very long time. So the age of the universe can be very, very large and it can be completely reconciled with the age problem. Later on, we have actually understood that the problem with this issue, the main problem was this number, because both Hubble and Lemaitre, the data that they had of Cepheids was incomplete in the sense that at the time, neither of them knew that Cepheids are actually not one class of objects. There are 2 classes of Cepheids. There are 2 kinds of Cepheids, and their pulsation versus luminosity relations are different. So if I use the pulsation luminosity relation of one class of Cepheids and apply it to the other class, I will get wrong luminosities and therefore wrong distances. And that is what had happened in this kind of plot. And the answer was eventually that this number should be downward revised by a factor 10. So instead of 500, it's a number close to 60 or 70 these days. Okay, so that is actually a much more elegant solution to the age problem than what Lemaitre was doing. But this is just to show that Lemaitre was constantly thinking of these things. Another remarkable thing he did in 1931 was that this coasting universe model, he extrapolated it backwards in time. This was the first time anybody had done this to a model of cosmology. Okay, go backwards in time and ask what happens. And he said that as you go backwards in time, the universe becomes denser and denser and denser, up to a point where the universe apparently becomes infinitely dense in this mathematical model, and therefore the maths must break down at that point. This was his way of saying that there might have been a beginning to the universe, and this was really the seed of what we now call Big Bang cosmology, because this was one of the ideas that came from Lemaitre. Another thing he did a few years later in 1934 is to suggest that this cosmological constant, which everybody had been using left and right, Einstein used it, Friedman used it, Lemaitre used it, everyone used it for doing various things. What is this constant? Where is it coming from? So Lemaitre pointed out that there may be a way of thinking of this using quantum mechanics. Okay, at that time, quantum field theory was not known, quantum mechanics was known. So Lemaitre was trying to think of this in terms of quantum mechanics and saying that there may be something like vacuum fluctuations, which may be the cause of lambda, cosmological constant. At the time, the mathematics was simply not there. So he just left it as a suggestion. And later, many years later, Zeldovich in Russia in 1968 rigorously calculated this within quantum field theory and tried to estimate this value. So what I hope you can see is that Lemaitre was a man who was many years, sometimes even decades ahead of his time. And not surprisingly, his views were very, very critically rejected during his own period, okay, especially this idea of the beginning, maybe because of his connections to the church, it's not clear, but people made fun of him, people like Fred Hoyle, etc. And the whole idea of the terminology Big Bang was a way of making fun of Lemaitre. Okay, and eventually Gamow and his collaborators brought back this terminology into the mainstream, and now we call this the Big Bang model, but it started with this person here. Good. So this is a little bit of human history. I can quickly take one or two questions before I go on to a little more physics.
Anyone has any question? Maybe not. So
we can maybe proceed.
yeah.
So I guess I'm at 1 hour right now.
Yes.
Okay. So I will try to.
Maybe you can take another 20 minutes or so.
Sounds fine. Sounds fine.
Yep.
So I may not do everything, but I'll try to give you some highlights. Yeah.
Okay.
Okay. So the next part of my story, I would like to focus on what is the universe made up of? What are the constituents of the universe? What is the stuff in the universe? Okay. And I'll also put this in a historical context because this history also goes back to the early days of cosmology. One of the things that we know exists in the universe, we've known it for a while, is this quantity called cold dark matter. So the terminology is not difficult to understand. Dark is just because we cannot see it. Okay, so what does it mean to see something? If a material interacts with light, then we can see it because light may fall on it, it may absorb the light, and therefore we see that it's eating up light, or it may emit some light, and then we see this light coming out of it. So any material, any atoms, any particles that interact with light can be seen. So the fact that dark matter is dark means that it does not interact with light. This is our understanding of what this material should be. So how do we know that it exists? We know it exists because of its gravitational influence, because it has mass and all mass gravitates. The cold in cold dark matter is related to its thermal distribution because we expect that the way it forms structure, which we will see a little bit later, we cannot tolerate the particle that forms this dark matter, whatever it is. It is not part of our standard model, but whatever it is, it cannot have a very large velocity dispersion. Otherwise, it would not produce the kind of structure that we see exists today. So this is the cold in cold dark matter. And the way this was originally discussed was in terms of a missing mass, in the sense that people took observations in which they expected some amount of mass, they did not see it. So the first such known observation was by the Swiss astrophysicist Fritz Zwicky, seen here doing something very funny. He's making fun of his colleagues at Caltech, probably. What he did was to take observations of galaxy clusters. This is in the early 30s. Okay, so this is well after Hubble, etc. We knew that galaxies are galaxies. There were clusters of galaxies. We knew how to take their redshifts. Redshifts are available. So what he did was to collect these redshifts of galaxies in clusters like the Coma cluster, shown here again. And so now there is this cluster of galaxies, and he assumed that the cluster is in some kind of mechanical equilibrium, kinematic equilibrium, or virial equilibrium. So he tried to apply the virial theorem. So remember, the virial theorem says that twice the kinetic energy of the system in virial equilibrium is equal to minus of the potential energy of the system. So you could equivalently think of as this equation here, expectation, the RMS expectation of V squared is equal to Gm by R, which is the potential energy negative. So the way Zwicky approached the problem is to say, okay, I have redshifts to all of my galaxies in this particular cluster. I assume that they are more or less in the same physical distance away from me, but they are kind of moving around each other. So there is a cosmological redshift given by the Hubble law, which gives me the average redshift of that entire cluster. And then on top of that, there are local motions, and local motions can produce a Doppler effect. Okay, so my total redshift, which I observe in my spectrum, is composed of these two quantities. One is the cosmological redshift, which is related to the distance away from me. And the second is the Doppler effect due to the local motion. And what he will now do is to say that given this cluster of galaxies and their redshifts, he subtracts out the mean redshift of that cluster and calculates the dispersion, or the RMS, root mean squared, of the remaining redshifts. And he converts that into a RMS velocity. Fine. So that's the V squared part on the left-hand side from the redshifts. On the right-hand side of the virial theorem, now G, of course, is Newton's constant, so that's known. There are two unknowns, apparently. One is mass and one is the size. So this is called the virial radius. It's the size of this cluster. The size is under control because you know the average redshift to the cluster, and therefore, because of Hubble's law, you also know the distance to the cluster. Now I know the distance to the cluster, and I know the angular size of this image in my photographic plate. So if I have an angular size and I have a distance, then I can convert it into a physical size of this object, because the angular size is nothing but the physical size divided by the distance. So knowing two of them, I can calculate the third. So I get an estimate of the size of this object from the angular size of this image. And using that, he tried to estimate the mass. So this is called the virial estimate of the mass of the object. And he found, okay, so he found some value for the mass. Then he said, these are clusters of galaxies. So these galaxies, let's sort of assume that more or less they behave like the Milky Way. There's no reason to believe that they are very different from the Milky Way. And in the Milky Way, the amount of light that is produced by galaxies has a pretty stable relationship with the amount of mass of stars. Okay, so it's like saying one mass of the sun produces one luminosity of the sun. Okay, so there is a mass to light ratio. For the sun, it is 1. For the overall galaxy, it may not be 1, but it is some number, and that number is more or less a constant for our Milky Way, across the Milky Way. And he assumed that that constant is also valid for all these other galaxies. So pretty big assumptions, but not terribly bad compared to, based on what we know later. So he converted the light that he observed from the stars of these galaxies into an estimate of the luminous mass that is present in these galaxies. And he compared his estimate of the virial mass to the estimate of the luminous mass. And he found that the virial mass is about 500 times larger than the luminous mass. So he said there must be some missing mass, and he called it Dunkel Materie in German, which literally means dark matter. So he invented the terminology dark matter. Now, there are many problems with this approach. Later on, I mean, people are already worried about, okay, how do you know that there is no other mass in the system? Okay, so one of the problems was that he did not know how much gas there might be in these clusters. So later on, in the 50s and 60s, due to X-ray satellite experiments, we know that such clusters also have a lot of hot gas. And that gas can be much larger in mass than the stars which are producing the light which Zwicky was measuring. But even if you account for that gas, the amount of mass does not reach what Zwicky estimated as the virial mass. The other historical artifact that happened here was, like I said, Hubble and Lemaitre. The slope that they had obtained for the linear redshift distance relation was 10 times larger than what it should be. And what that meant was that his masses were 10 times larger than they should have been. So he thought that he's getting a number which is 500 times larger than the mass in stars. Actually, it was more like 50 times larger than the mass in stars. And today, we know that despite accounting for all these objections, this discrepancy between the luminous mass and the expected gravitational mass, it remains. Okay, so I think we can confidently say that Zwicky was the first person to discover dark matter in the universe. The next person who did something remarkable in this field was, in this particular topic, was Vera Rubin. She was a remarkable person herself. She was one of the pioneering women astronomers in our field. She faced a huge amount of gender discrimination, despite which she managed to produce world-class and some may say Nobel-winning research, although she was never given the Nobel Prize. Okay, so her most famous work is based on rotation curves of galaxies, which most probably you have heard of. And she produced these kind of images. This is not from her paper, but it's from a similar kind of object, where you plot the rotational velocity of tracers of gas in galaxies which are far away from us, as a function of distance of these tracers from the center of the galaxy. Okay, so these distances you can see are measured in kiloparsecs. This is the typical size of galaxies that are tens of kiloparsec. In a Newtonian framework, you would expect that eventually this circular velocity as a function of distance should fall off, like 1 over root r. But what you see is that the circular velocity remains more or less flat, and therefore you explain it by saying that there must be some extra mass which I have not accounted for. And this is consistent with saying that there is missing mass in these galactic systems. So the remarkable thing here was that both Zwicky and Rubin had discovered missing mass. Zwicky said that this mass must exist at the scale of clusters of galaxies. Rubin pointed out that this missing mass is also missing at the scales of individual galaxies. And therefore, it is not a far stretch to imagine that this mass, whatever it is the same beast. It just exists everywhere, and you also see it in individual galaxies. You also see its imprint on clusters of galaxies. So this is dark matter. The other important constituent of our universe is a bath of radiation, which exists everywhere around us. It exists everywhere in space, and it was predicted by theory. Okay, so these were calculations that were being done by Jim Peebles and his collaborators at Princeton in the US. And they had been very keen on trying to detect this bath of radiation. They didn't know exactly what the temperature of this bath should be. Gamov and his collaborators had shown that there must be a black body radiation, and Peebles and company had tried to come up with ways of estimating its temperature from theoretical means and trying to detect it. And around the time that they were planning to start building an instrument of their own and writing up a paper on this, they were informed that two astrophysicists, Arno Penzias on the right and Robert Wilson on the left, who were in New Jersey, which is only about 50-60 kilometers away from Princeton. They were building they had built a radio instrument. They were taking measurements. They were trying to do very highly sensitive radio measurements of some balloon experiments and like scattering off of balloons, etc. And they wanted their noise levels in the radio instrument to be very, very low. So they had cooled their instrument using liquid helium. They had scrubbed their telescope antenna. They had shooed away some pigeons and removed pigeon poop from the antenna. They had done everything they could, and they found that there is residual noise at microwave frequencies, which they simply cannot get rid of. So someone basically realized that people should talk to each other. So Peebles and his gang realized that Penzias and Wilson have discovered this thing. They started talking to each other, and they very quickly convinced themselves that this is exactly what Peebles and company have been hunting for. So this was the discovery of the cosmic microwave background. The temperature using the brightness temperature was estimated to be about 2.73 Kelvin. Okay, and this won the Nobel Prize for Penzias and Wilson in 1978. Now the hunt for fluctuations in this background began, because here you can see that this background is like a uniform background, same temperature everywhere. But the same theory that Peebles and company were using to predict the existence of the background was also telling them that there must be fluctuations in this background, because without these fluctuations, you cannot form late time structure. Galaxies cannot emerge at late times. So there must be some fluctuations, but the amplitude of these fluctuations was unknown. One other historical thing I should mention is that the discovery of this background was a very important milestone for the Big Bang model of cosmology, because unlike the steady state universe, which was its competing theory, a Big Bang model actually predicted the microwave background, while steady state did not. So most of the community accepted this as being the solidifying argument in favor of the Big Bang model of cosmology. Okay, but back to fluctuations. So this hunt for fluctuation began, and it went on until quite late, until 1993. So there were experiments even before this, but they were not very clean. The cosmic background explorer, the Kobe satellite, was one of the first ones. This was a satellite experiment. And because it was not hindered by the atmosphere of the Earth, it was able to make very clean measurements. There were two primary instruments, there were three instruments. Two of them were relevant for cosmology. The first one was the one which measured the spectrum of this radiation. Okay, so the prediction was that this should be black body. And what was measured was absolutely amazing. It is shown here. The data points are from this FIRAS instrument. The error bars have been multiplied by a factor of 400 just so that you can see them. So this is the most remarkably precise black body known to human beings. no black body produced in the lab can hope to achieve this kind of precision. Okay, so this was another solid, very, very solid evidence in favor of Big Bang, that there was a perfect black body. Its temperature was 2.725 Kelvin. So this got one Nobel Prize. The second part of the same Nobel Prize was given to the detection of fluctuations, finally, using this other instrument called a differential microwave radiometer. It was a differential instrument taking differences in temperature in different parts of the sky, and it managed to produce this map and found that there are fluctuations in this uniform background, which are at the level of 1 part in about 100,000 or so, okay, 10 parts per million or so. So this was the first, this heralded the start of what is called precision cosmology, because once we had these fluctuations, new instruments, more sensitive instruments were built. For example, the Wilkinson Microwave Anisotropy Probe, another satellite-based instrument, much more sensitive than COBE and with much higher resolution. And now you can see that, if I flip back and forth, you can see the structure that you see, the noise kind of structure has gone down to much smaller scales. And now what one can do is these kind of statistical techniques that I was talking about before, 2-point correlation functions. So that's exactly what is done here. Now it is done on a 2D map rather than on 3D positions. And again, what you can see are there are some data points, and there is a best fitting curve, which is a model coming from the Big Bang model of cosmology, basically, and its extensions to describe the fluctuations in this cosmic microwave background. And you can see that the model produces a very nice fit. There are predictions not only for temperature fluctuations, but also for polarization fluctuations. All of that fits very nicely. So this WMAP instrument was one of the first in which you could start using the CMB to do cosmology, because I can produce predictions of this kind of curve, the red curve, with different values of my cosmological parameters. And I can do a chi-squared minimization exercise to ask which parameters best fit, and what are the error bars and so on. So this is kind of statistical inference started being done in this era of WMAP. And this was pushed further by the Planck instrument. Have got to even better resolutions, and now you can see the supreme quality of the data that was produced by Planck. This is kind of an overview picture produced by the Planck collaboration, where they compare their results with all the history of CMB experiments that came before them and around them. And you can see that the combination of all these experiments, and especially Planck at these large angles, gives you very, very precise measurements of what the CMB is doing. And you also pin down your model very, very precisely. Okay, so you're now talking about percent level errors in the model parameters. So this is the other important ingredient in the universe, the cosmic microwave background. There are some other ingredients also, which I will not have time to talk about. So what I will do is maybe very briefly, actually the number of slides also is now small. So I will briefly just discuss roughly how we think about the universe. Okay, so I am not going to show you equations. I'm going to flash some slides. The slides have equations, but the idea is not to go into the equations. You should think of this as pictures of equations. Okay, the point is not to understand the equations. The point is to get a feel for the kind of stuff that people do. So I wanted to also emphasize the role played by Jim Peebles, who got a Nobel Prize in 2019, basically for the huge corpus of work that he did, especially in the 1970s and 80s. He has been a guiding light for many people in the field of large-scale structure. The kind of things that people have been doing across time are first perturbation theory in the linear regime, where you assume that these CMB fluctuations are very tiny. They're 1 part in 100,000. So that is a very small number, 10 to the minus 5. So I can do perturbation theory and throw away everything but the linear term. Okay, so that's linear regime in which I can do some calculations. I can go beyond the linear regime and I can start asking how the theory behaves if I start keeping higher order terms. I can try to come up with toy models of growth of structure. I can do semi-analytical models. I can do numerical simulations. Peebles has contributed to almost every single aspect of these kind of techniques over the decades. More or less, this is how people think about how structure evolves in the universe. The simple idea is that gravity is attractive. Okay, so if nothing else, this is the only thing you have to remember. So now if I have a situation where I have small fluctuations in my mass, some places are overdense, some places are underdense, then the overdense places have more mass compared to the underdense regions. So if I have more mass, I will gravitate even more. The rich get richer. Okay, so gravity is attractive and unstable. So my overdense regions will eventually become really overdense, and they will collapse and become self-gravitating clumps. These are called halos, what Zwicky was calling clusters, okay, virialized objects. Now, in these objects, this is primarily made of dark matter. I have gas also in the universe. This gas will fall into the deep gravitational potential wells created by these clumps. As gas falls into these clumps, it starts heating up. Basic thermodynamics will tell you if I compress some gas, its pressure will increase, its temperature will increase. Once this gas heats up in its temperature, what will happen is that line transitions can be excited, because collisional excitations can become very important in very hot gas. And then I can start having line transitions where the gas starts emitting lines due to electronic transitions. Now, emission of photons through these line transitions will carry away energy from the system. If energy is leaving the system, then the system will cool down. So this gas, which was initially heating up, will now radiate and cool. If it cools, then its pressure goes down and it can condense even further because gravity wins. It's always a competition between gravity and pressure. Okay, so this cycle will keep going on until eventually stars will start forming at very high densities. These stars will be organized into galaxies. These galaxies will live inside these host dark matter potentials. And eventually these galaxies will merge when their halos merge, and they will form groups and clusters of galaxies. So this is how we think large-scale structure emerges in the universe. There have been many other approximations also, particularly by Zeldovich, who showed that, in fact, in a situation where I start with this kind of fluctuation, very simple approximation allows you to show that structures very similar to the large-scale cosmic web that I was showing you very naturally emerge. Okay, so all of this work was being done in the 1970s and 1980s. This is the flash equation slide that I was talking about. Again, no need to read everything. The slide will be available later for people who are interested. I just wanted to say that there is a lot of work that has been done in this field, and it continues to be done. There are many techniques, perturbation theories, analytical models, simulations, etc., etc. I will not go into these details. Please feel free to ask me questions or delve into this through the references given here. So what are the open questions that remain? So maybe in the next 5 minutes, I will...
Aseem,
yeah.
There are a couple of questions, so you want to take them now or after the talk?
Maybe it's better to wait a little bit, hold on to the questions because I'm almost at the end, then it becomes a little more relaxed.
Yeah, sure. Yeah.
Is that okay? Okay. So I just wanted to highlight a few open questions which are like big scale questions. So I will not speak about open questions in large scale structure per se. There are also many interesting things there, the kind of things I have been interested in doing. But to motivate you into the field, I think it is more interesting to talk about the super big questions. So there are basically two of them, dark matter and dark energy. Okay, so what one knows is that there must be dark matter. What one does not know is what is dark matter made of. Is dark matter cold dark matter like we were talking about? Or could there be some room for some thermal dispersion which you are not able to probe? So this might be called warm dark matter. Today we can do simulations of all of these things and check what are the impacts of these different assumptions on the large scale structure of the universe. So here, for example, visually you can see that cold dark matter produces very stipply, very corrugated kind of large-scale patterns of the density of mass, whereas this warm dark matter produces kind of smooth-looking things. And can we come up with statistics and ways of probing the large-scale, observed large-scale structure that can distinguish between these two? So this is a very important challenge in large-scale structure, first of all, and more generally in the field of dark matter astrophysics. We don't know what this quantity is. So a lot of particle physicists are interested in knowing what dark matter is, how to improve the standard model, or what are the other ways of thinking of dark matter, etc. So large-scale structure fits in very naturally into this big question of trying to understand what dark matter is. The other important question which we don't have a handle on yet is dark energy. I told you that Einstein introduced a cosmological constant for his own reasons. What I did not tell you is that in the late 1990s, it was robustly established that the expansion of the universe is accelerating. And it is very difficult to explain an accelerating expansion using standard mass and radiation, because gravity is attractive. So even if I set off a system expanding, because everything inside is attractive, I should expect that expansion to slow down. I should not expect that expansion to speed up. But the observations are indicating that the expansion speeds up. So in fact, the cosmological constant is our best bet so far, has been the best bet for explaining this acceleration. But we don't know why the cosmological constant has the value that it does. So people have been interested in asking whether the acceleration is due to a cosmological constant, which is just a constant, or maybe there is a function of time, at least some dynamical quantity there which might be doing the job. This unknown dynamical quantity is called dark energy. And the most recent excitement here has been, again, due to the same DESI survey that I mentioned before. The latest DESI data, also the first year data, but now also the DR2 data, are seeming to indicate that the model that you require may actually be different from a cosmological constant. So don't worry about this plot. What you have to understand is that this intersection of the horizontal and vertical line would correspond to the cosmological constant. And these are statistical distributions of the parameters in this space that are inferred from analyzing the data. And these distributions are not overlapping with the cosmological constant. So there are some tantalizing hints here that the universe, that the dark energy may not be a cosmological constant. I would say this remains to be seen, but this is definitely very exciting. The other excitement has come back in the guise of a question about the expansion rate. Let me quickly go back. Remember, kilometers per second per megaparsec. We said that they got the CFIDs wrong. It should have been closer to 50. People settled down recently, in the last 20, 30 years on a value. It's not 50, but it's around 60 or so, 60 to 70. Now, the observations have become so tight that two different kinds of observations are giving distinctly different results. One kind of observation is giving a number consistently around 70 to 75, hovering around 72. The other is giving a value which is closer to 67. Now, you might say 67 and 72 are not very far, which is true in an absolute sense. But in a statistical sense, because our data have become so accurate, that the error bars have become so small, that these two different ways of doing things are producing distinctly different results. Why is there this difference? Okay, there is a huge amount of literature on this. There is no convincing answer. Maybe one of these techniques is wrong in a very subtle way, which we have not understood, or maybe we have not understood the universe in a very subtle way. Either of these things could still could be true. So these I would like to say are open questions. The last, let me try to just motivate you into saying, okay, if I want to join this field and I want to start understanding the universe, what do I do? You should read books. Please don't stop reading books. Books, YouTube is not a substitute for books. Books will give you information at a pace which is tuned to you, and they will give you all the information there is in a very curated and structured manner. Studying a book is extremely important. I've collated here a set of books which I have found very useful across the years, and I've highlighted in bold some books which I have personally used as a student and also until now. And number one in this list, I would say, is Narliker's Introduction to Cosmology. This book has really stood the test of time. It was written in 2002 or so, earlier, I think. I've forgotten the year. I think it's around 2002. And it has really stood the test of time in the sense, it is a bit dated in the sense that it will not talk about very modern kind of things, two-point correlation function, etc., etc. But as an introduction to basic cosmology, I think it cannot be beaten. So I would warmly recommend the book. It is not a very large book, but it is very dense. But in typical Javian style, he will take you start to finish. You will think that, oh, it was only such a short lecture, such a short chapter, but you will realize that you have learned a huge number of concepts. Then there are these other two books which
So
are
actually, it
extremely...
was published in 2002 only.
Yes, that's right. Thank you. So then there are these other two books which I've highlighted, one by Scott Dodelson and a later version by Dodelson and his later PhD student Fabian Schmidt, Modern Cosmology. Extremely nice introduction to perturbation theory and large-scale structure, the fundamentals of large-scale structure. There is this fat book, Mo, Vanden Bosch and White, Galaxy Formation and Evolution, written by the leaders of this field. And it has everything under the sun as far as extragalactic astrophysics is concerned, including very nice introductions to cosmology and large-scale structure. There are also books by Paddy and Peebles, which are extremely good. So I would say if you have already had an introduction from Narliker's book, then reading Paddy's structure formation is an absolute must. And if you want to do structure formation and the statistics of large-scale structure, then this book by Peebles, Large-Scale Structure of the Universe, is the Bible. Yeah. So please read books. If you want to become a theoretical cosmologist, what are the prerequisites? This is a biased opinion, but this has stood, I mean, I have seen that this works. So this is what I would suggest. You should know all of your MSc level basic physics. Okay, this is extremely important. I would say instead of focusing on 6-month projects during BSc, I would do a reading project and go and study some aspect of physics in more detail. Okay, instead of trying to, trying to understand advanced concepts in those years, I would much rather focus on basic concepts because there will be time to study advanced concepts. When you are past the MSc level, you want to start delving into the field, the kind of things you will need are stuff like basic general relativity. And if you're interested in early universe, you will probably also need quantum field theory. You will definitely need a good handle on mathematical methods for physics, Fourier transforms, differential equations, techniques for solving these things, etc. You will also, nowadays, it is impossible to do any kind of cutting edge research without having a good grasp of statistics and statistical techniques in cosmology. These are applicable to both theory and data. You might think that it's only useful for analyzing data. Actually, statistics can also be incredibly useful for building theoretical models. You cannot live without some familiarity and I would say proficiency with at least one programming language. If you don't know any language, I would say definitely do Python. But if you already know something like C, for example, I would say that is already a very good starting point. And then you can pick up Python along the way. These days, everybody's writing in Python. I have written these things in italics in the sense that you don't really need them on the first pass, but it's good to have them. So one good thing to have as a theoretical cosmologist is a sound grasp of observational constraints. Because this is what I'm saying for prerequisites. In terms of possible career paths, this is a very conventional career path. There may be unconventional ones also, which one can explore. But this conventional one involves a bachelor's degree, either as a BSc or a BTech. In fact, BTech is also okay, as long as you have a robust understanding of physics and mathematics at the undergraduate level. Okay, so I have seen good BTechs come out of engineering institutes and then do cosmology. You should also have, like I said, a knowledge of MSc physics. So having an MSc under your belt is usually a good thing. In nowadays, what is happening is MScs are being offered with specializations in astronomy and astrophysics, which can be a very useful thing to have. The other kind of MSc that might be interesting is specializations in data science. Okay, but it should never be at the cost of physics. So your physics knowledge should absolutely be there. And then a 6 months or a little bit more specialization in one of these two is also welcome. Finally, you can do a PhD. There are several institutes in India. I've listed a few here. I am at one of them at Ayuka. Or you can also target institutes abroad. Then the world is your oyster. So I've also listed the typical timescales that one is talking about here. And usually after a PhD, if you want to do serious research and want to join somewhere as a permanent faculty or something like this, you typically have to spend a few years of postdoctoral research. Best to do it outside so that you see the world, you see how different people do science, and then you come back and work here. Okay, so this is what I had to say. I think I've gone much over time. I'm happy to stay and answer questions if you want.
Okay, so unfortunately it's online, so we cannot, I mean, if people will clap, it won't be audible, but let us thank Aseem for a fantastic talk and also telling you about how you should proceed with your studies. So maybe we can quickly take a couple of questions. So there is one theoretical question which I'll take up at the very end, but there are
Maybe, yeah, maybe I stop sharing my screen so I can also then maybe see.
okay.
Okay, yeah, go ahead, go ahead.
Okay, so the first question is, how are we still able to measure the CMB if this is the first ever light that is emitted? And the other related question regarding CMB is that what is the meaning of the bright spot and the dark spot?
Okay, very good, very good. Both are interesting questions. Let me just, this thing is hung. What's going on? No, for some reason I'm unable to move this thing. Give me a second. My screen is visible. There is some
Yes.
on the screen. Okay, something.
Desktop.
Let me stop sharing quickly and I will just share once more. Okay. Okay, share screen. Good. Am I back?
Yeah.
And you can see I'm moving
Right.
my slides. Yeah. Great. So let's go back to the CMB. Okay, so why can we see the CMB? Well, CMB is a collection of photons. The theory tells us that in the very early universe, photons and let's say electrons were scattering off of each other. So a photon would meet an electron, it would scatter. Then very quickly it would meet another electron, it would scatter. Okay, so by scattering, what happens is that if you remember, the energy of the photon can have some changes, etc. Momentum can change, but the direction can also change. So the photon, because it meets many, many electrons, it is basically doing a random move. It never really travels in a straight line. This situation proceeds for a while, but then the universe is expanding and its temperature is falling. Once the temperature falls enough, what will happen is that these photons, which are able to not only scatter off of electrons, but initially they were so energetic that they could take a hydrogen atom and ionize it. Okay, so these high energy photons existed when the universe was very hot. As the universe expands, it cools down, and these high energy photons are not high energy anymore. Their energy becomes less. So now that the energy is less, hydrogen can form. And once hydrogen forms, it becomes neutral, right? Hydrogen is neutral. So the electron and the proton, their collective charge is not seen by the photons anymore. Photons cannot talk to neutral particles. So photons cannot scatter off of hydrogen. So once enough hydrogen forms, the universe becomes transparent to photons. So imagine I am the last photon that exists before all the electrons went into hydrogen, if such a state happened. Then I scattered off of an electron just yesterday. And suddenly today I realize that there are no electrons left anymore. Everything is in hydrogen. So I am now free to do what I was doing, meaning that I will just keep going in a straight line. And there is nothing to stop me now. Okay, until I hit some other piece of material which is able to absorb me. And we are here in the orbit of the sun with an instrument pointed around, and one of these photons comes and impinges on us. So these are the photons that we see. And such photons can be seen coming from arbitrary directions because the theory says that these photons were everywhere in the universe and they were going in every which way. So from all directions, there would be some photons that came to us. Not all photons from there would come to us, but there would be some that would be directed to us. So that is the way we see photons, even though they were emitted very early in the universe. They have been traveling for all that time. The other thing is, what is the difference between, is that right? What is the difference between these hot spots and these cold spots?
Yeah, what are these dark and bright spots?
Very good. So what I was trying to explain is that here, the first observations told us that there is a uniform bath of constant temperature everywhere in the sky. So this image is supposed to be a mole-wide projection of the sky around us, right? You must have seen projections of the map of the Earth, where India will be here, and then South America will be stretched out like that, and so on, right? So this is like the map of the sky seen from inside, from us. Okay, and this stupid cartoon that I have made is to represent that the earliest predictions of the CMB were that it should be uniform in the sky. So its temperature is being depicted as this color, and its temperature is the same in all the directions. Now, the refined version of the theory tells us that the temperature is not exactly the same. It should have some fluctuations, and these fluctuations were detected. So there are these differently colored spots, and what they are representing is that the mean temperature of the universe has been, of the CMB, has been subtracted out. And these red and blue spots are telling you, the red ones are telling you how much higher I am compared to the mean, and how much lower I am compared to the mean. And the amplitude is set in such a way that the reddest spot is the maximum typically that I see, and that maximum is typically around 1 part in 100,000. So these are microkelvin fluctuations that you are seeing in the temperature. So that is what the color means here. And what has happened across time is that our instruments have become better, and they have been able to resolve the difference between temperature of very nearby spots on the sky. So that is why as you go from this image to this image to this image, the stippled pattern goes to smaller and smaller scales, because you can start seeing differences between very neighboring pixels. Okay, so that is what these hot and cold spots are. So what physically this is representing is that there is a region of the sky where the temperature was slightly higher. There is another region where the temperature was slightly lower. Within this region, there are other more fluctuations. Okay, the lower region overall is lower, but if you zoom in, you can see that some regions are very low, some other neighboring pixels are slightly low, and so on and so forth. So there is this structure of fluctuations everywhere in the sky. This is very nicely described by a Gaussian random field, and the statistics of this Gaussian random field are captured by this 2-point correlation function, which is predicted by the theory and now measured by observations.
Okay, so I'll take 2 more questions which are related.
Yeah.
One is, can you explain the word cold in cold dark matter once more? And the other is how the halos are formed during cooling.
Okay. So the cold of cold dark matter, I did not explain much. It is related to the distribution function of this particle. Maybe there's a simpler way of understanding it. I don't know whether people are familiar with neutrinos. Okay, so neutrinos are very light particles, and they typically travel, once they are produced somewhere, they interact very infrequently with ordinary other kind of matter, and they travel very fast at speeds approaching the speed of light, because they are very, very low mass objects and they can travel very fast. So imagine a production mechanism for something like a neutrino particle. And this production mechanism has produced a bunch of these neutrinos with randomly chosen directions of velocity. So what will the overall distribution of these neutrinos look like? It will basically look as if they have a temperature, because there are random motions of these neutrinos. Each neutrino is traveling in whichever direction with a very high speed. And this overall randomness is captured by an RMS fluctuation whose value of velocity, whose value will be very close to speed of light. So this will be a very hot fluid that you have created. So now what one imagines is that maybe there's a controlled way of doing this in the theory, in particle physics. And you may want to imagine models where you're not producing neutrinos, you're producing a different kind of particle in which this RMS value of the velocities is much smaller. Okay, so these are elementary particles still with a much smaller typical kind of random velocity. And random velocity, RMS velocity is basically like a temperature. So you're saying that these are particles with a lower temperature. Okay. The limit of this is a particle which can be produced in its distribution with temperatures approaching 0. Okay. So the theory tells us that the temperature that one produces is connected very tightly to the mass of the particle that you're producing, which intuitively makes sense. If I have particles like neutrinos, which are very low mass, I can afford to have them at very high temperature. If I make very, very heavy particles, then their temperatures will be very low. So in advanced theories of particle physics, like supersymmetry, for example, there are natural candidates for what such particles can be. And that is what led to a lot of excitement in the 1980s in the particle physics community, that there may be natural candidates for what dark matter is. Okay, so this is, I hope, the intuition behind what cold means. And for a cosmologist, cold dark matter is basically the idea that if I didn't have cold dark matter, then this kind of pattern would not look like this. Where did that picture go? I had this image here. So imagine that that pattern is equivalent of the right-hand side picture, where those fluctuations, this stippled kind of fluctuations, is being reflected by the stippled kind of density that you see in this simulation here. If dark matter were not cold, if it were slightly higher temperature, the fluctuations might end up looking like this. Okay, I don't know whether it is really visible, but these are slightly smoother than this. Okay, so if this were the case, then the observed CMB would look smoother than it does. And then we would be able to tell that the particle had a certain temperature. So this is like an observational way of saying that the dark matter that we're talking about must be cold. Sorry, there was another question which I forgot.
Yeah, how the halos are formed during cooling.
Okay, so maybe there is there was a nomenclature issue. What I meant to say was these halos are formed out of gravitational collapse, because there is an initial stage which is like this CMB stage, 1 part in 100,000 fluctuations. That's represented in this image. Now, this is an overdense region, underdense region, very small fluctuations. But wherever I have slightly larger overdensity, gravity will attract more matter. Okay, and once gravity attracts a little more matter, that region has that much more matter. Now, gravity can attract even more matter. So gravity has this instability. Once you feed it a little bit, it just goes on eating and eating and eating. So this gravitational instability is already enough to produce these things called halos, because eventually what will happen is you will not just keep collapsing to infinite density. You will not form black holes or something. You also have random motions, random angular momenta, and those will stabilize the system in a kinematic sense. And you will achieve what Zwicky was calling virial equilibrium. And so these virialized clumps will form. So that is what I meant by halos. Okay.
No, I think the question relates to this year.
I'm coming.
Gas heats and cools.
Yes, exactly. So what one is talking about here is that there is gas here. The gas, of course, also has mass, but the gas has a temperature as well. So what would happen is that if I just had the gas, you could argue that the gas could also do the same thing. Now, why not create halos out of gas? Problem is that gas has a temperature, and then once you start compressing the gas, its temperature increases, or rather its pressure increases, right? Because it has an equation of state. So once the pressure increases, it can hold itself against gravity. And therefore, it will not collapse further. And that would be a problem, because then you will not be able to form stars. You will not be able to explain where galaxies came from. So dark matter helps you because it gives you a pre-decided set of potential wells which are already very deep. Okay, because dark matter was not interacting with ordinary matter. It is dark. So these potential wells became very deep. So they gave the gas a chance to collapse quite far in, because gravity kept winning until the gas became extremely hot, like million Kelvin hot. Okay. At that point, the gas will start radiating, because at 1,000,000 degrees Kelvin, you will have things like ionizations happening, for example. Electrons will start, talking to, you will have collisions between atoms, which are so energetic that they will knock off electrons from the outermost orbitals. Okay. And, or for example, an electron will fall into an atom and release a photon, or some kind of ionization kind of reaction may happen, where a collision happens with high enough energy that ionization occurs, and I have a photon released in the process. So electron also goes out, photon also comes out. These photons that are released in all these high energy interactions between the elements, those photons can, under certain conditions, escape from the system. Okay. So what is this system? It had gas, it had a temperature, therefore it had some energy. But now I'm saying that photons are leaving. But photons have energy, right? So if they're leaving the system, then the total energy of the system has gone down. Total energy has gone down means the temperature has decreased. Temperature decreases means pressure decreased. Pressure decreased means gravity starts winning a little bit more. So the system can compress a little bit more. Okay. Then again, it can heat up. Then again, its pressure will go up. It can radiate, cool, and then again go through the whole cycle again. Okay. So this is a continuous process that happens. And eventually things like turbulence, etc., take over, where you reach very, very high densities, which would otherwise not have been possible if these original dark matter clumps were not there. I don't know if it directly answers the question, but I hope it clarifies some of the ideas.
So, okay, very last two questions.
Yeah.
One is, why do you think that there are different types, or why do we think that there are different types of dark matter? That is one part. The other part is, why does the nature of dark matter influence the CMB?
Okay, very interesting. Both are very interesting questions. Why do we think there are different kinds of dark matter? The way I would address this issue is that we don't know what dark matter is. So now the simplest thing that you can say is that dark matter is one kind of particle and we don't know what it is. So if we don't know what it is, maybe it is something like a cold dark matter particle, like a relic, what is called a neutralino in supersymmetric language, etc. Or maybe it is like a warm dark matter particle or a sterile neutrino or something like this. But that would still say that this is one kind of dark matter. And the reason we are allowing for such possibilities is simply our ignorance, because we simply don't know what dark matter is. We have not detected it in the lab. All of our high energy collider experiments have not told us what dark matter is. So now really the hope is from cosmology and extragalactic astrophysics to try to pin down something about the nature of dark matter. And what I tried to, in a cartoon way, show here is that by understanding differences on very large scales between the distribution of dark matter in different models, you can try to take this forward to the observations and say, okay, if dark matter is cold, my observation should look like this. If dark matter is warm, my observation should look like that. My observations look like something, so maybe I can tell the difference between these two. The current status of these questions is that there is no very strong evidence of anything other than a cold dark matter-like particle. Okay, so there's no, we don't have really a good handle on this yet. Sorry, the other question was?
How does the dark matter influence the CMB?
Yes, very nice. So one of the primary things that the dark matter does is to allow the CMB fluctuations to remain at 1 part in 10 to the 5. Okay, so what one can show is that suppose there were no dark matter in the universe and you wanted to explain these CMB fluctuations. Now you have observed them at 1 part in 10 to the 5. Yeah, so that is an observational fact. Suppose the only thing that the universe were ordinary matter, which eventually became hydrogen gas and which eventually became galaxies. You can ask the question, how long would it take for galaxies to form in a universe where there is no dark matter and the CMB fluctuations have been observed to be 1 part in 10 to the 5? The answer to this question would be that galaxies should not have formed at the present time. You would have had to wait for, I don't know, 10 billion years more or something for galaxies to form. The age of the universe, it would simply not make sense to have galaxies today. What dark matter does, and the reason for this is that the expected fluctuations here for the given amount of matter should have been much deeper than 1 part in 10 to the 5. They must have been much stronger. They should have been 1 part in something like 10 to the 3. Okay, only 1 part in 1,000, not 1 part in 100,000. So one way of putting it is that the fluctuations in the CMB appear to be 100 times smaller than they should have been if you want ordinary matter to explain all of the mass in the universe. What dark matter does is again to provide potential wells, which have been growing since the time that the initial conditions of the universe were set, which were at a very, very early epoch. Okay, that epoch I have not spoken about. It's the epoch of inflation. So from very early times, much before the time that the CMB photons were released, Dark matter has been there. It has not been talking to photons, but it has been gravitating. So dark matter had more than enough time to produce dense potential wells, which were of the order of 1 part in 10 to the 3 and not 1 part in 10 to the 5, 100 times stronger than this. And the reason why the ordinary matter was not able to do that is because it was talking to photons, and photons are like, super fast, express trains. They don't allow you to sit still. If you are going to collide with a photon, you will get kicked in a random direction with a very large velocity. So even if you start off trying to become very dense, soon some photons will come and disperse you completely. Okay, so these ordinary matter densities cannot be very large, but dark matter is allowed to be large, sitting underneath, not being visible here. So it very nicely explains why the CMB can have these kind of fluctuations and why galaxies can exist today. Yeah, so that is what dark matter does to the CMB. It provides an underlying skeleton of potential wells in which the CMB could happily exist.
Okay, so just the very last question.
Yeah.
This is from one of our faculty colleagues. What is your take on the JWST data, especially the high redshift structure formation and little red dots?
Yes, thank you. I did not go into JWST at all. Apologies for that. Of course, JWST, the James Webb Space Telescope, is taking a remarkable set of observations. Recently, it's a remarkable instrument, first of all. It has been doing many interesting things for extragalactic astrophysics, especially our understanding of early galaxy formation. So one of the first puzzles that came out in the JWST results got many cosmologists excited. Basically, the idea of the result was that one is seeing galaxies which are much more massive at high redshift, that is at early times, and they should not have existed with that kind of mass at such early times. In standard cosmology, this was the initial claim to fame of that result. There are several issues with this. So this is the result. Now, what are the possible solutions? Theoretical cosmologists will go to town saying cosmology must be wrong, and therefore let us try to break everything and figure out what new we can do. However, the extragalactic astronomer will tell you that there are many other questions that one has to resolve first. And then there is an in-between set of questions also, which are very interesting. So let me talk about the extragalactic astronomer kind of questions. This is the fact that astrophysics already at epochs where we have studied it well, even there are very high uncertainties in our understanding of galaxy formation. It is by no means a done deal that we understand everything about galaxy formation, let's say at redshift 6, at redshift 3, at redshift 2. There are many uncertainties. And especially if you imagine something like, I have data which is going out to a certain point, and now I'm trying to extrapolate what it will do in a regime where I have never before taken data. Okay, so I had astrophysical models, and at every point along the way, I had to calibrate these models and introduce some ingredients and tune some other parameters so that my models always match the existing data. Now, of course, these models are tuned to match the existing data. If I want to use them to predict what happens in a regime where I did not yet have data, those will be extrapolations. So what has happened right now is our simplest extrapolations are getting it wrong. Okay. So one thing one has to at least ask is whether there are further updates that one needs to make in our understanding of astrophysics, which will try to explain some of these things. So some of my colleagues here are very interested in this problem. They are asking whether formation of dust in galaxies can be a way of understanding these discrepancies without touching cosmology. Cosmology is like the last thing you will touch. Okay, so that is one important thing that astrophysics has to be explored in much more detail than it has been done for the time being. Not to say that the results are not exciting. Absolutely, they are exciting, and they have definitely generated a lot of discussion in the community. The other very interesting aspect of these observations is statistical in nature, because JWST by its very nature is a small field instrument. It is, of course, a much larger field of view than its predecessors like the Hubble Space Telescope. But it is primarily an instrument which is detected to see things very far away in relatively tiny regions of the sky. it's a simple money game, right? Because I get a finite amount of time on my telescope. I have to decide whether I look in the same direction and collect lots of photons so that I can see further and further away. Or do I compromise on the number of photons from one particular direction and spread out my money in observing over a large area of the sky? So all the surveys that I showed you, they have been going in the wide first, depth later kind of philosophy, where they go wide at a certain depth, they get results, then they convince the funding agencies to give them more money so they can push the depth further and further. JWST lives in a class of instruments which does exactly the opposite. It started with Hubble and now it has reached JWST, where you start by saying, I want to know things at very faint luminosities and very large distances. And I will then slowly increase my field of view from there. So Hubble had a very small field of view. JWST has substantially more field of view. But this is even then much smaller than the kind of volumes we are talking about for the large-scale structure surveys. So one problem with having small volumes is that there is a lot of fluctuation that you can expect if you only look at one particular part of the sky. So of course, JWST team knows all of this, and their survey strategy is to slowly cover multiple fields, which have been targeted based on previous surveys where you know that, okay, there may be higher or lower densities. So you want to overall get a representative sample of the large scale density structure that might have existed at those redshifts. But if you only look at one such field of view, you are looking at a possibly biased region of space where the density might be unnaturally high compared to the mean density of the universe at that time. And this can also lead to, if you now compare the results that you get there with a prediction from theory, which is based on the mean, then you are not surprisingly going to get numbers which are substantially higher. So this so-called cosmic variance has not yet been fully beaten down in the existing JWST result, but it is slowly getting there because the number of fields is increasing. The data that are being used are slowly increasing. So I hope that that addresses this issue. And of course, we will see how things progress in the near future.
Okay, so I think we have to stop at some point in time. So let us again thank Aseem for this wonderful talk and also for patiently taking up so many questions and answering them. And so yeah, thanks a lot, Aseem. I had a couple of questions, but maybe I'll ask them later on.
Sure. I'm happy to have been here. Thank you all.
Okay. Bye, everyone.
Bye. Okay, Rakesh, I will sign off.
Yeah, sure. I'll write to you.